So let's say we have a cone of this height. Okay, and this is the height I'm talking about. All right, and the question says the uh, radius for the circular surface of this is 2 centimeter. Okay, and the rate of change of the height, let's say it's 5 centimeter per hour. The question might ask you, I'm just giving you a sample. The question could be even more complicated. The question might ask you, find the, oh, sorry, it shouldn't be R, it should be T. Find the rate of change of the volume. Okay. Can you imagine something? What could be done here? Can you think of anything here? Anyone? Out of your head, can you imagine what could be uh, done here? What can you do? No one? Or if you're trying to say anything, uh, let me check if I can hear you, because often it's the technical issues. Uh, Hopefully it's it's all right. Okay, so can you imagine a way, or just if you just eyeball the question, can you think of anything that could be done here? What do you think?
You could probably try and find d of t using what you have up in the second level. So you at least know part of d of v over d of t, maybe?
I didn't get your point. Could you please repeat it? Maybe you're saying it right. I just didn't understand.
So what I'm saying is you could try to find at least d of t from d of h over d of t somehow, some way, right?
Like this, from d as dh of dt, you're saying can find this.
Maybe.
So this is an operator. It has to work on something. dt of what? That's the question. Only this value cannot be uh, calculated because this is an operator. It doesn't have any particular value of itself. Anyway, good guess. You know, just trial and error. So let me give you a hint. If I say I know the volume 1 over 3 pi r squared h, I know the volume, right? Now uh, can you think of anything that could be done? Just eyeball the question. The reason I am giving you this uh, or giving you time to think about it is so that you can actually start building up this process. Because when this type of question will be given, the hardest job, if there is any, will be to understand what should I do. The calculus part, I believe, is much easier because you have actually done more complicated problems than this. Okay, so now let's look at the question. The question says, hey, find dv dt for me, right? I already have v. How can I get to dv dt from v? Can you imagine? Anyone? Now with the hint. Okay. So since the v is here, I can just take the first derivative of it in terms of t, dv dt on both sides. d dt of 1/3 pi r squared of h. Do you agree? Because that's what I'm looking for. Before going for the calculus part, any question from this? Any question from this? No question at all?
So to take into account the fact that the height is changing, would you have to plug in the dh over dt into the h at some point?
That's a good question, because I have dh dt, right? And I have fixed this r, so that means it's not really changing, or in other words, it's a constant on this particular problem. So if I find the derivative of this thing, my assumption would say, since these are all constants, right, I'll have a dh dt for this h. We're actually going to that in the next line. So 1/3 pi r squared, all of these are constant. So the only thing we have is the derivative of h in terms of t. Do you agree? Because only that thing is changing in terms of time. And we know if we have a constant times a function, we can actually keep the constant outside and find the derivative of the function. That's what I've done here. All of these are constants. I kept them outside and just found the derivative of the function, let's say. Although the entire part was the function anyway. Put someone in the waiting room. Okay. Do you agree with the calculus part now? I mean, how did I get this? Entire part, of course, entire calculus part. If you're wondering, how did I get this? Again, all these three in blue arrow here, all these three are constants. So we know if we have a constant time a function or uh, uh, which is actually changing in terms of which we are finding the derivative. On this occasion, only h is changing because it's been already given. So other than that, the rest of the three, obviously 1/3, it's a value. It's definitely a constant. Pi is always a constant. It has a fixed value. And for this problem, I did say my r is given. That means it's not really changing. For a fixed r, I'm trying to find the rate of change of the volume. So that means my r is also fixed for this particular problem. So if all of these are fixed, or in other words, all of these are constants, I can keep these outside and find the derivative of only that thing which is changing, and that's h, right? So the derivative of h in terms of t is th dt. Do you agree? And then if we can just plug in the values, 1/3 pi will be kept as it is. R was 2, I believe. Yeah. So r squared will be 4, and dh dt is 5. So if we can simplify it, we can write it like this. Not really simplifying anyway. 20/3 pi. So this is the rate of change of the volume for this cone. Any questions on this? Take your time and see if you have any question, okay? No questions at all? Okay. All right, now let me give you another example, and then I'll give you a chance to work on um, a problem like this, okay? Um, before that, let me pull up the syllabi and see what we are supposed to do today. I think it's 3.11. Maybe maybe you are on track right now. Just give me a second, or if you have the syllabi, you can pull that up. All right, the tentative schedule, June 14th. Yeah, we started 3.11. Okay, all right, that's good. Because I would like to spend some time on this topic. This is not easy. I'm not saying it's really difficult, but often uh, it's difficult to uh, visualize things straight away. Often you need some time, right? Okay. Now let's see this example, and then I'll give you a chance to work on a problem like this. Okay. Let's try a more complicated one. Okay. Again, if you're working on a problem like this, whenever you start working on assignment 3.11, the shortcut is, or rather, you can have this at the back of your head, that somehow or other you are going to find some derivatives here. You are going to play with derivatives. Okay, you are going to differentiate at least one, maybe more variables, and then play with the values. Okay, so let's see an example like this. Okay, let's say you have a wall, okay, and there is a ladder like this, okay, and that's your wall. That's the wall, and this is the ladder, okay. The ladder, it's actually touched here, and I actually know the length of the ladder. Let's say it's let's say it's a 5 feet ladder, and this is leaning vertically, okay, or rather I would say this is leaning like this on this wall. It's leaning. Okay, all right, now if I say, hey, I can uh, I can start pulling the foot of the ladder away from the wall at a rate of, let's say, 0.2 feet per second. Then the question would be, how fast is the top of the ladder sliding down the wall when the foot of the ladder is 8 feet from the wall? Okay, now what does the question says? Let us see. Let us try to visualize this. Okay. So first of all, what I'm saying, I'm starting to pull this ladder. Okay. So that means this is going down this way. This ladder is going down this way. Right? Can you see that? So that means you are slowly and slowly just pulling the foot, I would say. This is my foot, let's say. So let me show what's actually going on. Initially, the ladder was like this. Okay. Now, since I have pulled it, in the next second, let's say, the ladder is actually here. If I keep pulling it, the next second it might be here, right? Can you imagine what's going on? That's the first question. So the question says, I've started pulling the foot of the ladder from the wall at a rate of this. Okay. And the question is, how fast is this going down this way? Let me use another color. The rate of change here. How fast the ladder is going, or rather sliding down. That means this direction. Okay, this direction. Because initially, if you remember, the ladder was here. The ladder was here. Then it came here, then it came here. So it's sliding down, right? The question asks you to find the rate of change of that sliding down. Okay, and you are given one more clue, which says the foot of the ladder is actually 8 feet from the wall. 8 feet. Okay, now the first job in our hand is to set up the equation, set up the question. That means in the previous problem, we had a cone, and we know the formula for the volume of the cone, and we actually took the derivative in terms of t, which saved our day. But what should we do now? It doesn't look like a cone. It doesn't look like anything. But there has to be a formula lying somewhere, right? Or hiding somewhere, which you need to find, and then you can use the concept of derivatives. So for that, we need to understand what the question is saying. Let me draw the problem again. So this one is, let me use another color. This one on red is the ladder, okay? And this one in blue is the wall. Okay, and the length of the ladder is given, which is 5 feet. Okay, and I shouldn't say 8 here. I should say rather 4. I should say it's 4 feet. All right. Anyway, and then what's this? If you can understand what's this, then your job is actually done. This is the length of, or rather I would say the distance from the foot of the ladder from the wall, or rather to the wall. The distance between the foot of the ladder and the wall. So which length it is that? What do you think? If you can understand it, your problem is half done.
Would you find the rate of change of that length, so the ground length, and then use the Pythagorean theorem to find the height?
Very good. So this 4 feet is basically this length. Do you agree? Because as I said, this is the foot of the ladder. This is the wall, right? This bluish line. And it says the ladder is 4 feet away from the wall. The foot of the ladder is 4 feet away from the wall. So this length is 4 feet. Do you agree? This is the most important thing. If you can understand it, the rest will be pretty simple. Okay. Now we have, yeah.
Hey, sorry, what if the triangle turn upside down?
Sorry.
What I'm saying is that what if the triangle turn upside down? If the ladder or the ladder turn upside down?
If the ladder what? Sorry. I think the internet is unstable.
Yeah, what I'm saying is that what if the ladder turn upside down? Will it be convinced? Will it be somehow deceptive if the ladder turn upside down? What if the question state that we are trying to look for the feet, the distance of the feet from the wall. What if it turn upside down?
What if it turn upside down?
Yes.
I'm confused. What you're trying to point out here. I mean, why would it turn upside down? That's the first question. Do you mean like this? Let me try. If that's the wall, do you mean if the ladder is uh, uh, leaning like this?
Yes, yes, that's what I'm saying. What if you turn something like that?
Well, well then on that occasion it wouldn't mention the foot of the ladder, maybe, because if you are sliding the ladder like this, then you must be standing here somewhere in the first floor, because otherwise you can't really slide it down, like this. Still it would be the foot, I guess, because the top of the ladder is here. But I don't think you'll see a question like this, because for that, whoever sliding it uh, along the wall has to be in the first floor, or has to be somewhere up from the ground, because this is the ground, right?
Okay,
Let's
because
see.
I've seen the question like that. That's why I'm asking.
Okay, let's see if we can generate a question like that. But yeah, for this type of question, you'll definitely need more information. Yeah, let us finish it first, and hopefully we can generate one like that. I understand your question. Yeah. All right. Now, since it looks like a right triangle, and we know the value of these two sides, if I say, hey, I can actually use the Pythagorean theorem here, do you agree with that? I can actually use a Pythagorean theorem like this. I shouldn't write r squared though, because r often signifies the radius. Let us use another value. Let's say z squared. Okay. And why am I using this? Because I can't really see anything else which could be a resemblance of this. Only the right triangle looks pretty similar. And I'm just saying this on behalf of you. I know that I need to use it here because of my experience. But what if you are doing it for the first time, or maybe it's one of the uh, early stages of when you're doing it. So you maybe just go for trial and error. I'm just uh, trying to see what happens if I imagine this as uh, the Pythagorean criteria. So if I do that, let's say that's my x from the ground, that's my y, the height from the ground, this is the feet of the ladder from the ground, this is the length of the wall, and z is actually the length of the ladder, right? We know the Pythagorean theorem, right? Okay, now we have the rate of change of the x. That means this point 2, if you remember, was how fast uh, my uh, not my the foot of the ladder was moving from the wall, right? I was actually pulling the foot of the ladder away from the wall at this rate. So if I say the length of the, or I would say the distance of the foot of the ladder from the wall is x, what's this? If you can understand it, then half of your job is done. The other half, you have already figured out the formula. Now you just need to understand what is this. Again, this is the rate at which I'm pulling the foot of the ladder from the wall. What do you think this could be? If you try to denote it with something. Anyone? If this is x, if the length from the foot, if the length of the foot from the wall is x, what if I say this is actually dx over dt? Do you agree? Again, this is probably the hardest of anything, if there is any. Do you agree that it's actually dx over dt?
I've got a question about that actually.
Mm-hmm.
So since you're moving that on the X, would you also be moving like the same rate down the Y? Or is it different because they're different heights or different lengths?
So obviously, since I'm moving it in this direction, there will be a rate of change in this direction as well. And this is what we are actually going to find. Because if you remember, when I started the question, I said, how fast is the top of the ladder sliding down the wall? That means we actually want to find the rate of this change. A good question.
Okay, but those rates would be different though?
It could be
Like it's
different.
not
You
0.2.
never know. It could be same. It could be different. But there is no guarantee. We need to find that. Okay. Now we have again. We have the Pythagorean theorem. What? We do it separately. Okay. We know this length z. We know this length x. We don't really know this length y, but we're not really concerned about that anyway. We know the rate of change in this direction. We know dx over dt is 0.2. I'm just setting up the entire question to see what we're actually looking for. And we want to find the rate of change of this. So these are the informations we have, and this is what we need to play with. What do you think we should do? So again, if you remember the last problem, we actually start with the formula and find the derivatives accordingly. So what is the formula on this occasion?
Would you have to find the derivative of that Pythagorean theorem
Very
formula?
good.
The Pythagorean theorem.
So
For y, it would be the square root of 5 minus x squared.
yeah, but I don't really need that
Okay.
now. If I need that, I can do that. Yeah, definitely. You can actually find the explicit version for y. Yeah, definitely. I can do that. And this is g squared. And this is basically 5 squared to the 5, right? This is given. This is given. That's my g, right? Okay. Now, first of all, we want to find the derivative of x squared plus y squared. And of course, whatever we do, we need to do that on both sides, all right? Okay, now we are back to calculus. What's the derivative of x squared?
2x.
Only 2x? Is there anything else? Obviously,
Should be 2x plus 2y.
no, I'm talking about the x squared part only, the first term, x squared. Obviously, the derivative of x squared is 2x, but is that all? Or do we have anything in addition to that?
No.
Anyone else? Think about it. Try to eyeball in terms of what we're trying to find the derivative, and then use your intuition. This is the calculus part, by the way.
Would the x be whatever the x is plus the rate of change per time?
And why?
Because it's changing by 0.2 centimeters per time, and we're trying to find it in regards to time.
No, just because you have this information, it doesn't mean that we have to use it somehow. I mean, what's the basic reason? If you think that there should be a dx over dt somewhere, what's the basic reason for that? It can't be a reason that the information is given. There has to be some basic way, right? I know why you are trying to say this, because if you don't have a dx dt here, then we might not be able to use that. But what's the general way? What's the general thinking behind
D
it,
over dt of that equation.
of this equation?
I think I confused myself.
No worries. Anyone else? I mean, let me go back. So we are trying to find the derivative of this equation, right? So we have taken, since we are trying to find the rate of change, that means we are trying to find the derivative in terms of t, right? Because you can see, oops, I think I should write hour here. I should have, yeah. Oh, I have given per second, so I should give here per second as well. So you can see even eyeball from the units. So this feet per second means we are trying to find the derivative in terms of t. So we have taken the derivative on both sides in terms of t. Any question from this before I move any further? Any question from this? No questions at all? Okay, now we want to find the derivative of this x squared plus y squared. So let's do it one by one. Since we have a plus in between, so we know using the sum rule that we can find the derivative of these two separately, and then we can add those. We don't need to consider these together, right? It's not the product rule. Rather, these are two different terms. Okay, so now we can concentrate on x squared. Let's forget about y squared. So what's the derivative of x squared? So we know the derivative of x squared is 2x. Do you agree? Do you agree? But that was actually in terms of x, not in terms of t. The derivative of t squared in terms of t would be 2t. Now, can you imagine what I'm trying to say? What I'm trying to do here? Anyone? Let's give it a try. This x squared is not, we are not really trying to find the derivative of this x squared in terms of x. It's actually in terms of t. What should we do in that situation? In this situation, I would say.
Wouldn't it be 2x, the derivative of x over the derivative of t?
And why? I mean, there has to be a reason behind it.
To say, do you want us to say we are going to use something like an implicit differentiation?
Not really, because I'm just considering x squared. Okay, let me say this without wasting any more time. I know this is the first time you are seeing this, so maybe you didn't see the insight. So what if I say I need to use the chain rule? Because if you remember, this formula was for x squared, and if we had anything in place of that, we actually imagined that as x and then multiplied the derivative of that, right? So if it was t squared, we would have written a 2t. No worries with that. Since we are finding it for in terms of t, it's not really a t squared, but we can imagine it as a t squared. If it was a t squared, we would have written 2t. Since it's a x squared, we can write 2x, but it's not exactly that t squared, all right? If that's the case, we write the derivative of what we imagined in place of that t. In place of this t, we imagine this x. So this is the derivative of x in terms of t, and we need to multiply it. Just using the chain rule, nothing else. Do you agree? And same goes for this. For y squared, we can just imagine it here. So for y squared, it's 2y, but it's not exactly the t. So we need to find the derivative of that in terms of t. Do you agree before I move any further? If you agree,
Mr. Ake, I agree with your mathematical expression, but during some of our homework in implicit differentiation, this kind of problem come up that was solved in implicit differentiation way without using the chain rule.
I can't really tell you right now. Once I set up the question, I can tell you better. Okay, but using the chain rule and implicit differentiation at the same time, you'll see, yeah, you'll definitely see some questions like this, where you need to use both on the same question. You might need to use the rules separately. There is no hard or fast.
Yeah. What I'm saying is that we can choose one, not using both rules on the same question. We can choose one. Some of the homework that I was doing currently, there's a question like this there that under the implicit differentiation. So what I'm asking is that, can we use the chain rule, or we can just stick to the implicit differentiator to solve this? Can the rule of an implicit differentiation solve this question? That's what I'm asking.
So if you can find the solution using just one of those, if you are actually doing it in the right way, then you are more than welcome. But I don't think you'll be able to do that. I'm not sure which question you are asking about, but I can understand your question. You are asking whether you are allowed to do using just one of those, right? You are not.
Yes.
So you are not willing to use both the rules in the same question. But if it requires, what if it requires? That's my question. In some cases, you will actually need to use both on the same question.
Okay.
Yeah, it actually depends on the question. Okay, what's the right hand side? What's the derivative of 25?
0.
Exactly, it's a constant. So it doesn't matter in terms of what we're trying to find the derivative. It's a 0. Okay, now we're trying to find the derivative of y in terms of t. That means the rate of change in this direction when I was sliding down, right? Yeah, this one. So we are trying to find the value of this. Let's isolate it first, okay? If we isolate it, dy dt, that means we'll change sides for this, so it will become negative 2x dx dt. I'm just changing sides for this to isolate this, or you might rephrase it or reiterate it as I'm just adding a negative of this to both sides. That's why I have a negative on my right. Whichever way you think you can iterate it. And then we can isolate it completely. I'm just dividing both sides by 2y. Right? And this 2 and 2 will get cancelled. So we'll have a negative x over y dx dt. If we plug in the values of this, we'll get the value of our desired, we'll get to our desired solution. All right? Now, we know the value of dx dt, which is 0.2, I believe. Yeah. We know the value of x as well, which is 4. We just need to find the value of y. Okay, now we can use that formula again and isolate y. So y is basically 25 minus x squared. If I just take the square root on both sides, I'll have 25 x squared, 25 minus x squared, right? And since it's a length, you can clearly imagine a length cannot be negative, so you can actually remove this. Sorry. So this will be my y. And since x is 4, I believe, yeah, x is 4. So if I plug in the value of x here, I'll get y. So 25 minus 16.
That's 9.
9. So y is 3. Now I can plug in the value here. This is my scratch work. So negative x is 4, y is 3, and dy dt is 0.2. So if I use my calculator, I'll get 4 times 0.2, which is 0.8 over 3. And if I simplify it further, I'll get a 0.27, a 267, negative, of course. Point 267 centimeter per second. Okay, so this is my answer. Any question from this? Take your time. No question at all?
I kind of have a question, but it's
Yeah,
more like
sure.
a reiteration. So up earlier in the equation when we were doing more of the calculus kind of stuff, when we had to multiply the derivative of x squared, you know, we had the 2x and we had to multiply it by d over dt of x.
Mhm.
Do you see what I'm kind of talking about?
Yeah,
Is it safe to say that it's kind of like, I mean, this is how I'm kind of picturing it in my mind. It's almost like converting it to that d of t because we're trying to find it in terms of t. Is it kind of safe to say that we're trying to convert these values of the derivatives to the t, to the time?
So it actually depends. Yeah, you might remember like this, but it depends because I might ask you to find the derivative in terms of some other variable. So it actually uh, depends what I'm trying to find, or rather, I would say, in terms of what I'm trying to find the derivative. So since I'm trying to find the rate of change, obviously in terms of time, that's why these are t. These are t's. So we're not really trying to convert anything, because the rate of change is definitely, obviously, in terms of something, but it doesn't need to be t all the time. It depends on the question. You can actually eyeball it from the question, because I say the rate of change, or I would say I was actually pulling the foot of the ladder at this rate, 0.2 centimeter per second, or did I say feet? Anyway, the unit will be given. Okay, so you need to eyeball it from the question. We're not really converting it anyway, but yeah, again, you might remember it this way. I don't think there is any harm in doing that, but yeah, we're not really converting it.
Okay, thank you so much. That made it a lot clearer when you explained it more. Thank you.
Any other questions from this? I know it looks complicated in the first place, but if you do one or two more problems, which we'll do, it will make more and more sense. Okay, and no worries, this is not going to be a part of this exam. I mean, what we have tomorrow. Okay, any other questions? Any other question you have? If you don't have any other question, let's take a break for 5 minutes, and then we'll practice a couple of more. Okay. All right. So let's meet at 10:19. Okay. Now the next question is, let me pick up another question. Okay, yeah. So this time we have a circle. Very good. We know the area of the circle. We know area or rather circumference of a circle. So this is going to be a known workplace for us, right? So often familiar situation gives us a head start. We actually feel more confident that, okay, since it's a circle, maybe uh, I can crack this code. I can crack this question. Okay. All right. So let's say we have a circle. Let me draw one for you. Okay. And the question says the area of a circle increases at a rate of 6 centimeters squared or square centimeter, however you say, per second. The area, of course, the area of a circle increases at this rate. Shouldn't draw another circle though. All right. Now, the question is how fast is the radius changing when the radius is 4? How fast is the radius changing when the radius is 4? That means they have given us r equals 4. They want me to find how fast is the radius changing when the area is changing at this rate. Now, what should we do?
You have to use the formula for an area of a circle.
Very good. Again, that's why I say the known situation, a familiar situation gives you a head start because you actually know what are my possible things to work with. So, excuse me, since they have given me the rate of change of the area, and I know, fortunately, I know the area, right? When the radius is r, I know the area of this particular circle has to be pi r squared. And the rate of change of the area is given. I can eyeball it from the units. The squared sign signifies it's the unit of area, and this is the unit of time. So area over time, that means this is this. And obviously, whatever you do, we need to do that on both sides. So we need to take ddt on our right as well. Excuse me. First of all, do you agree with this step? Do you actually feel that it's why it's done?
Yeah, it's starting to make sense now.
Is there anyone who has a question? I mean, why do we need to take the derivative in terms of time on both sides? No question? Let's carry on then. So dA dt, no worries with that. That's the value is actually given, that is 6. Now, the derivative of pi r squared, what should we do?
Can you take the pi out and since it's a constant,
Very good.
yeah, and then you do the derivative of r squared since that's what's changing?
Okay, so for r squared. Now what should be the derivative? Entire part of the derivative. The complete derivative of r squared in terms of t.
Would it be 2r and then dr over dt?
Very good. Yep. Using the chain rule, right? If it was t squared, I would have written a 2t, and that would be the final answer, but it's not exactly t. So using the chain rule, we imagine that this is my t. So using the chain rule, we can write 2r for this r squared. And since this is not the t we wanted to have, we need to find, or rather write the derivative of that and multiply it. Okay, and r is given, r is 4, dA dt is given. The question wants you to find how fast is the radius changing. What's that? If the radius is r, how can I denote this English phrase, how fast the radius is changing, with a mathematical notation? What should be the notation if the radius is r? If I say it's dr dt, do you agree? Because dr dt is the rate of change for this radius. That means the way the radius is changing, right? Dr dt. It's really important to understand what it actually wants you to find. First of all, do you agree that we're actually trying to find dr dt? Do you agree with that? Is there anyone who is still confused why it should be dr dt? Because understanding the question is really important. Otherwise, you might be doing it in the wrong way. So, since we're looking for this, we'll try to isolate it and plug in the values later once we are done isolating that. So we want to get rid of this entire part, right? So if I want to keep dr dt on my left, I want to get rid of this. That means I'll divide both sides by that. So 1 over 2 pi r dA dt. I'm just doing algebra here, nothing else. No calculus here. The calculus part is done. I've just isolated this. So that's why I've divided both sides by this. And then I've written dr dt on my left and the other term on my right. Okay, just simple algebra, nothing else. And now I can plug in the values since it has said the radius is 4. So 1 over 2 times pi times 4, and dA dt is, I guess, 6. Yeah, it's 6. It's, if we simplify it, 8 pi, or we can write 3 over 4 pi. That should be our answer. Do you agree with this? Take your time, okay? Okay, now I'll give you a question um, which you can work uh, in groups, uh, and then I'll try to solve it. Okay. All right. Let me write the question for you so that you can see this on the screen and probably um, work on that later when I create the group, right? Okay, so let's say the area of a square decreases at a rate of, let's say, 0.2 feet squared per second. What is the rate of change of the side when the side is let's say 4 feet. Okay, so that is your question, and you need to find the solution of it. And for that, I'll once again create a breakout room. So first of all, the area of a square is decreasing. So straight away, you can imagine we're looking for a square, right? It doesn't look like a square though. Let me try it again. Okay, yeah, definitely. Now it looks like a square. And it says it is decreasing at a rate of 0.2 feet squared. I mean, the area, of course, you can eyeball it even from the units at this rate. Now, what is the rate of change of the side length when the side length is 4 feet? So these are all 4. Do you agree? Since it's a square, right? These are all 4. Do you agree? Okay, the next question would be, which formula should we start with? What is this? And what are we looking for? I mean, the notation. To understand the notation is really important again. If the area of the square is S, what's this? What's this rate of change of this area?
ds over dt.
ds over dt, okay. Okay. Oh, sorry, we're talking about area, right? My bad. I think I should say the area is A. We generally do that. So yeah, if the area is A, using your idea, I can say it's dA over dt, right? We generally denote the area with A, volume with V, and and radius is obviously R everywhere in the world, and S with S for length. We generally do that. You can change it, but whatever you do, you need to mention it. Okay. All right. So let's say the sides are S. So the next question would be, how can you denote the rate of change of the side? Anyone? The rate of the change of the sides? How can you denote it using the notations we have? Just give it a try. If the side length is S, what's the rate of change of the side?
Would be ds over dt.
ds over dt, exactly. So we're actually looking for ds over dt. Do you agree? Okay. Now, the next thing is which formula we should start with to solve this problem.
I mean, the area of a square is base times height, yeah?
Is based on what, sorry?
Base times height.
No. We have a precise formula for the area of the square.
Be S squared.
A squared, exactly. For a square, the area is actually the side squared. So the area of the square is S squared. Yeah, for a rectangle, it's base times height, I know. Base time, not base times height, I would say base times width. But for a square, it's precisely the side squared. Since you don't have two lengths for it, there is only one length. Okay, now, obviously, we know we need to take the derivative in terms of t. Let's do that. dA over dt equals to ddt of s squared. What's the derivative of s squared in terms of t? That should be pretty easy. We have already done it a couple of times. Anyone? What's the derivative of s squared?
Two S.
Only 2s?
Two S times ds dt.
Exactly, 2s times dstd. Because this is not exactly t, so if I write 2s, we need to write the derivative of s in terms of t. Again, if you're finding the derivative of another variable, other than this, you need to have the derivative of that multiplied with that. That's what the chain rule says, right? Okay, so we're looking for DSDT. So we'll isolate that. I'm just doing some algebra here, nothing else. So we'll divide both sides by 2s. So 1 over 2s dA dt. And we know the values. S is 4 and dA dt is 0.2. So 0.2 over 8, which is, if I use my calculator, 0.2 over 8 is 0.025. Okay. And this is my answer. This is the rate at which the side lengths are changing. Oh, I guess I got it wrong. Yeah, slightly wrong. Can anyone eyeball a mistake in my calculation? I've already found one. That's good though, because I've done a mistake which is pretty common and done really, I should say very frequently. Just eyeball the question. Shouldn't it be negative 0.2 because the area of a square is decreasing? Do you agree? The area of the square is decreasing. That's why it should be negative. So it should be negative 0.2. All of this should be negative. And it actually makes sense. Why? Just imagine a square. If the area is decreasing, the sides rather, have to decrease as well. There is no way, if your area is decreasing, there is no way the sides will be increasing, right? Just try to imagine your entire area is decreasing. That means the sides are also decreasing. Do you agree? So that's why it has to be negative as well. Now, any question from this?
So when we do the equation like that, would we write dA over dt is equal to negative 0.2? Yeah,
Here?
yeah,
Yeah, it's negative 0.2. Yeah,
I missed that, sorry.
no problem. Yeah, it's really difficult to see. I can understand. That's why I've used a different color, because there is hardly any space there for a negative sign. Okay. Now, if you don't have any question, let us move to 4.1 and just to briefly see what we have on offer in that. Okay. So that's from 3.11. The idea is same. start with the formula which you think that fits best using the informations you have. Take the derivative. Make sure you, if you need to use the chain rule, make sure you use it, and then just do just a little bit of algebra, and that should be fine. That should take you to your desired result. Okay, but again, the crucial part could be to understand these notations and using the chain rule properly, because I was a TA for Calculus 1 back in Reno when I was doing my master's, and I have seen, I was a TA for 3 semesters for Calculus 1, and I've seen so many students missing this part, missing this additional part of the derivative. It's really important, and it's really easy to make a mistake like that. Okay, so keep an eye on the derivative once you finish that. If you're finding the derivative of any variable other than the given one, you have to use the chain rule. That is, you have to write the derivative of that and multiply it. Okay. All right. Let's start 4.1, and I've already provided you the slides last night. Unfortunately, it actually came in the wrong order. That is, if you start that slide, if you open the slide, it actually starts with 4.9. You need to go all the way down to see 4.1. I'll try to fix it today. Hopefully, I'll be able to do that. And if I do that, I'll definitely upload the updated file. Okay, no worries. Okay, let me start sharing the screen. 4.1. Okay. Okay, where is 4.1? Point one is at page 143 of that slide, if you're still looking for it. Okay, at page 143, and here you go, maxima and minima. Again, that's really a very good type of content in the derivatives or in differentiation. It's really interesting, and it's fun to work with. Okay, maxima and minima. Okay, we'll see the definition later on. Let me first show you a graph. Okay, yeah, here you go. So when you are given a graph, it's easy to understand where is your maximum value and where is your minimum value, right? It's easy to see that. But what if a graph is, a function is given, a graph is not given? So we want to see the graphical representation today, and hopefully we'll see the algebraic approach the next time when we meet on Wednesday. Okay, so if you can eyeball the graph, excuse me, let's say we have a graph for the function 4 minus x squared, and it's actually for all real numbers. You can see from negative infinity to infinity. So for all real numbers, we are trying to find the value, or rather the maximum and the minimum value for this function. Okay, so if we can eyeball the graph, we can definitely see the highest peak is at this point, right? The highest value is 4, and it's at x equals 0 because it's, you can see it's on the y-axis. Do you agree? Since it's on the y-axis, we can say the maximum is at x equals 0, and obviously we can also eyeball the maximum value. It's actually 4. Can you see that? Okay, now what if I say, can you eyeball any minimum value? Can you? Just take a look at the left graph, okay? Excuse me. Take a look at this graph. Can you eyeball a minimum value from this? Anyone? And the answer is no, right? Because you can see the graph actually keeps going on. It doesn't really stop. It keeps going on. And for a minimum value to exist, you need to have an end point there, or you need to have a change of direction there. If it keeps going forever, you can't really have an ending to it. At least we can't really see any change of direction here. It keeps going in the downwards direction, and there is no end point either. So there is no minimum value for this graph on this domain. I mean, from negative infinity to infinity. If we precisely change its domain, if we give you a particular domain to work with, then you might have a minimum value. You never know. Let's look at this graph. For this one, from 0 to 2, you can see, I mean, if the domain is from 0 to 2, that means we are only considering the values of x from 0 to 2. And for this part, the graph looks like this. If we consider this part, if you see there is an endpoint, right? So this has to be the minimum value, the minimum point of this graph. Because the graph doesn't really go beyond this, so this has to be the lowest point. This has to be the minimum value. Do you agree? So graphically, we can actually eyeball and see where is the minimum, where is the maximum, and whether it actually exists or not on a certain interval. For example, if I say on the interval 0 to 2, 0 and 2 not included, that means for x equals 0 and for x equals 2, the graph doesn't have a defined value. It actually ends before that. Okay, it starts right after x equals 0 and it ends right before x equals 2. So this 0 and 2 with this parenthesis, if you remember, it means 0 and 2 is not really included. If that's the case, you can see there is no real minimum and maximum value, because this can go really, really close to 4, and this can go really, really close to x equals 0, but I don't have these values included. I'm not really talking about limits. I need to have a precise value for it. So I can say that there is no maximum or minimum value. That means you need to have a defined value at your uh, minimum or maximum point. The maximum point is definitely this, but we don't have a defined value. The minimum point is definitely this, but we don't have a defined value either. So that means you need to have a defined value. Okay. All right, so this is the graphical representation of finding minimum and maximum, but we want to find it algebraically. And let me tell you, it's really fun to work with that. And obviously we'll be using the concept of derivatives on this as well. And we'll see this on Wednesday. So when we meet next time on Wednesday, after the exam, I want you to just go over this slide 4.1. It starts from page 143, okay? Just go over this slide and just briefly see if you can generate a question from this. Okay. All right. So